on temperature and kinetic theory. And this is also related to for the video on absolute zero, which is the actual credit video, which it seems like most of you have already taken that, which is still open. So we're going to get into the concept of temperature. You look at the video, there's been temperature, measuring temperature. What do we have for temperature, temperature scales and stuff? What do you mean by temperature? So the three main scales are the Fahrenheit scale, which we know and use, the centigrade scale, and the Kelvin scale. All right, so Fahrenheit, Celsius, Kelvin scale. All right, now Fahrenheit scale, we're not going to do much with this, but the relationship between temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32 degrees. So if we have a temperature of 0, that will correspond to a temperature Fahrenheit of 32 degrees, and so on. All right, temperature of 100 is 212. All right, so that's the relationship in those two. All right, Celsius scale developed by Anders Celsius, as you know, is now set so that the freezing point of water is 0 and the boiling point is 100. So it was made intentionally for that purpose. Now, the thing about this is that this allows for low temperatures below 0. So we're going to need, eventually when we get to the gas laws, later on in this chapter, we need a scale that actually has no negative numbers. We'll talk about that a little bit. So we have the Kelvin scale, and the temperature of Kelvin is temperature Celsius plus 273. And what this means is that, so a temperature Celsius of 0 is a temperature Kelvin of 273. And for a temperature Kelvin of 0, this is a temperature Celsius of minus 273 degrees Celsius. Keep it as, this is what we actually call absolute zero. It's the lowest possible temperature you can reach. And in the same breath, temperature Fahrenheit is minus 459 degrees Fahrenheit. So those are absolute zero in the three different scales. We're really not going to do anything with converting Celsius to Fahrenheit. It's handy to know as far as certain things, like room temperature, 68 degrees Fahrenheit is approximately 20 degrees Celsius, things like that. Okay. Most of the world uses Celsius as their wet meteorological scale, but this is, we still use Fahrenheit for that. Okay. All right, so you can read as far as that's concerned, standard temperature scale. All right, so that's a little bit there. All right, so moving on here. There isn't really a whole lot to this chapter. The next section we do is 13.4, which is thermal expansion. And this will be either dealing with a solid or a liquid. All right. We're not going to deal with gases. Gases deal with the gas law, the ideal gas law. So we're talking about solids or liquids that are contained and have a different specific volume or length depending on what you're trying to measure. So we talk about measurement, and an example might be, say this meter stick was made out of steel, right? Say we have a 1 meter, so it's made out of steel, and we have the temperature is at 0 degrees Celsius, right? So a cold day, and we warm it up till it's relatively hot. So let's say a temperature of 30 degrees Celsius, which is probably about 90 degrees Fahrenheit. At this temperature, let's say the length is 1.00 meters, L, and we're using the same notation the book has, a little L. All right, what would be the length of that steel ruler? Again, we're taking this to be steel instead of the wood it obviously is, but using steel because wood has different properties of expansion. What would be the new length? All right, well, for that, we're going to use the relation of delta L, the change in length, is equal to alpha, which is a constant depending on the material, times L naught, which is what we'll use this, times the change in temperature. So this is a constant, coefficient of expansion, which I'll show. All right, there's coefficient of expansion. All right, this is from the table 13.1, near 20 degree, but it's approximate. And so what we have for steel, as we have from the table, so from table 13.1, then alpha is 12 times 10 to the minus 6th. So that's in parts per degree Celsius. So what would this mean then? All right, and we have delta T is 30 degrees Celsius. So delta L, which would be the change in length, would be 12 times 10 to the minus 6th times 1.000 times 30, which would be, let's see, 360, 3.6 times 10 to the minus 4th, or about 0.34 millimeters. So L would be L naught plus delta L would be 1.00036. So a little less than a millimeter. That's why, I mean, to be accurate, we'd actually have to have this to 4 decimal places or more to do that, to be able to measure it. So it's a very small amount. The amount it would actually change would be a third of a millimeter. So it'd be almost imperceptible unless you were measuring it with good precision. So that is how we calculate where alpha is coefficient of linear expansion. So this is only expands in one. We're only worried about the direction in one direction. It would obviously expand this way, and this way, as far as that's concerned. So there's examples of there. Now, next thing we're going to do is then, is look at volume expansion. All right. So this is only valid. This expression valid only for solids. I mean, it's irrelevant for liquids, for anything, gases obviously, or liquids. For liquids, because it doesn't expand this way. We can only measure the volume expansion because the whole thing expands. It doesn't expand in one direction because it takes up the size of the container. In that case, all right, I'll leave this up here with this expression. In that case, we have a slightly different expression. And in this case, we have this delta L is alpha L naught delta T. All right, for beta is coefficient of volume expansion. Okay, and in that case we have delta V is beta times V naught times delta T. All right. And what we see here is the temperature for most cases, in both cases, is the change in length is proportional to the temperature. The same thing here, change in length is proportional, change in volume is proportional to the volume. Change in volume is proportional to temperature. Not everything works that way. Water, we'll get to that. Water is unique, and it's unique in the sense that, which actually makes life possible, is that water, if we look at volume, V, and temperature, it's mostly linear until we reach a point of about 4 degrees Celsius. Then it actually starts to expand again. And because of that, water is at its densest at 4 degrees Celsius. Right? That's kind of why when the water at the bottom of the lake starts to get colder and colder, once it gets to the point of below 4 degrees, it starts rising top because it's less dense again. And this is why ice is less dense than water, particularly cold water, because when it's going to be cold, you know, if you have ice, like icebergs, the ice is going to float because it's less dense than water. If that was the case, if it was like this, then what would happen is ice would freeze and would sink to the bottom, and oceans would freeze from the bottom up, lakes would freeze from the bottom up. And for an ocean, basically what you'd have is they'd be solid because there's no way, there's no heat at the bottom of the ocean. So it would be solid from the bottom up, and basically life would be impossible. So it's because of this fact that life is possible, and it's one of the unique characteristics of water. All right, but that's just the case there. All right, so if we're looking at this expression, all right, and let's do an example, which I always like to do. Again, these are from the table. Liquids have a much higher coefficient of expansion than solids. And let's take an example of, we have, say, 40 liters of gasoline. And it comes out at, let's say, 10 degrees temperature, not unusual, say about 10 degrees Celsius. Okay? And we now let it sit in the sun. It gets really hot. The temperature in the car and then the gas tank goes up to 40 degrees Celsius. Okay. Right? What would change it? If we top it off, so we have 40-liter tank, we top it off exactly. What would happen to the gas? Would it make any difference? We saw with this, it's almost imperceptible. You raise this 30 degrees, and it changes almost an imperceptible amount. Well, gasoline has a coefficient of volume expansion of 950 times 10 to the minus 6th. So what we would have here, in this case, is delta V would be 950 times 10 to the minus 6th times 40. So our answer is going to be in liters. Whatever unit this is in, that is what that'll be. So if this is in meters, that'll be meters. If this is in liters, that'll be in liters. If it's cubic centimeters, it's just a fraction of what it is. Times 40 times 30. All right, I'm going to need a calculator. So we have we end up with delta V would be 1.15 liters. That's quite a bit. 1.15 liters, that's how much you would lose from that raise in temperature. So that's why you should never top off a gas tank, because it comes out relatively cold. Once it starts warming up, it's going to start spilling over unless you're driving right away for a relatively long distance. That's why they say never top it off, because that's exactly what's going to happen. So that's the idea of thermal expansion, whether it's for a solid, you're only talking about one direction, or volume, or we're talking about liquids. Right? This also works for solids, but generally we're referring only for liquids for this expression. Okay. All right, moving on here. And what we have is the last part of this chapter. And what we have here then is all right, basically 13.6, which is the ideal gas law. All right, and this goes back to a long time. I mean, Boyle's law, Charles' law, Robert Boyle in the 1660s realized that gases, their pressure, you have a container of gas, you can measure the pressure in the gas, all right? So if you have a pressure gauge and you can measure its temperature with a thermometer and you apply heat, he found out that the pressure was proportional to the temperature. All right? So that's what we led to the ideal gas law. Because what you find is what he realized is you drop the pressure lower and lower and lower. When the pressure became zero, the temperature would become zero. So they were able to figure out what the absolute zero would be just by plotting pressure versus temperature for gases at reasonable temperatures that could actually achieve, and realize you extrapolate it down, it would cross to 0, 0. So this led to the ideal gas law, and what we have here then is, I'm just going to give it to you, and I'm going to do it from a chemistry viewpoint, is PV equals nRT, where P is the pressure in atmospheres, V is the volume in liters, N is number of moles, T is in degrees Kelvin, obviously, and R is the gas constant, which for this case is 0.0821, and I'll put in the correct units: liter, atmosphere per degree Kelvin mole. Right? So that's the ideal gas law using this expression. I mean, physicists use a different one, but since most of you chemists, biology man, this is the expression we're going to be using. So P is in atmospheres, V is in liters, N is in moles, temperatures in degrees Kelvin for all of them, and then this is the ideal, this is the gas constant. Right? As far as that's concerned. So for all these expressions, you're generally going to be given what you see here is that you display a graph, and you can see this with no other problems. If we plot P versus T, and this will be a constant, N is, we're going to assume that N is the number of moles, we don't lose any. Then if we keep V as constant, then P is proportional to T. Increase P, increase T, you get increase V. We increase the temperature and keep the volume constant, the pressure constant, then P constant, and that increases linearly. It may seem contradictory if you increase it, keep the pressure constant, but to keep the pressure constant, then the volume has to get bigger and bigger and bigger. If you keep the volume constant, the pressure will go up. And then finally, if you plot pressure versus volume, we'll do more of these things and keep temperature constant. this is related to Boyle's law, we end up with the inverse one. So if this is constant, this whole right side is constant. So if P goes up, V goes down. And likewise. So we end up with an inverse relationship, and then P is proportional to 1 over V. So if you double the pressure, you're going to cut the volume in half. So this is relationships related to the ideal gas law, as far as that's concerned. And you can do some expressions related, problems related to that. So this is part of section 13.6. We're not going to do anything in section 13.8 on the physics one. I'll put it up, but we're only going to be using this expression for problems. But in 13.8, we have PV equals NKT, where in this case, P is in newtons per meter square. Everything here is in SI units. This is in meters cubed. This is the actual number of particles. This is what we call the Boltzmann Constant. And this is temperature in degrees Kelvin. So this is the only one that stays the same. It looks very similar to this. This is what we use in physics a lot, is this one. If you're dealing with individual particles, then you use this thing. But for gases, in general, we use this expression. And that's section 13.8, which we're not going to get into. The last section here we'll be doing for this next test is a little bit on kinetic energy. All right, so this is section 13.9. So I'll leave that up for a second. And in this case, for 13.9, all right, this is the part of kinetic theory, 13.9, temperature, and kinetic energy. Now, if you haven't done the video, Absolute Zero, looked at the video, done the quiz, I would encourage you to do that because it gives you an idea of the concept of what we mean by temperature and how we measure. What is that actually measuring? Basically, all temperature is measuring is the motion of the molecules. We arbitrarily call temperature, measuring degrees, but it's actually a measure of the individual motion of the molecules. And what we have kinetic energy, remember that's 1/2 mv squared. So if we have a molecule with some mass moving at some speed, like a gas, right? And they're all moving around different places with some speed. We measure that energy, kinetic energy, by this expression, 3/2 kT, or for an individual molecule, where this is what we call the Boltzmann Constant. So this is the actual mass of a molecule in kilograms. This is speed in meters per second. This is the Boltzmann Constant, 1.38 times 10 to the minus 23rd. And this is the temperature in degrees Kelvin. So for this is relationship. So there's a linear relationship between the kinetic energy and the temperature. All right, so that's how that works. So basically what we're saying is you double the temperature, you double the kinetic energy of a gas. Now in reality, there's always a distribution, not all molecules have the same thing, but there's actually normally a distribution of temperature, speed, temperature, and number, and it actually follows more of a curve where the average is where we get this expression, but some are going to be higher, some are going to be lower. Now, what's interesting here is that the lighter the molecule, the faster it's going to be going to have the same temperature. So if you look at, say, hydrogen and helium, if you look on the periodic table, light molecules. So for them to have a specific temperature, because they're extremely light, they're going to be moving very fast. And because there's a distribution, some of these will be moving very fast. And actually, some of them were moving so fast, they escape from the Earth's atmosphere. Given enough time, you always get some leaking out. Well, this pile is going to get smaller and smaller and smaller because the fast ones always keep escaping. They don't all escape at once. So what happens over a period of time, the lighter molecule, the faster ones escape, the total number eventually slips away. And so because of that, there is no hydrogen or helium in atmosphere. All right? All of the hydrogen we have in the atmosphere is basically combined with oxygen to make water vapor. All the helium we have is basically contained with uranium, natural gas deposits, because helium is a byproduct of uranium radioactive decay, so it's a very slow process. So there's none of these in the atmosphere. Be nice to be a hydrogen, because then you could do hydrogen fuel cells very easily, but basically there is none. So the only way you can produce hydrogen is by splitting water molecules into hydrogen and oxygen. So that's chapter 13 as far as that's concerned. You can look at that. I will then next week do chapter 14 and finish up the summary for that, and then do review for exam 5.